Hey guys, welcome back to Conquering the JavaScript Interview. In today's video, we're going to dive into a colorful challenge that will have you hoisting your flags high. Get ready to sort your way to success with the Dutch national flag problem. This vibrant technique will not only have you sing red, white, and blue, but it'll also help you fly your interviews at full mast. Oh, I kill myself with these puns. I think that's the most work I do in my videos is coming up with puns for the intro. Anyway, that's if you're wondering why there is a Dutch flag in the flag of the Netherlands in my thumbnail for this particular video, it's because this particular algorithm is a very common one you see across a lot, like every programming interview ever will probably have someone that's gone through this problem. It is sorting an array of 0, 1s, and 2s, aka the Dutch national flag problem. So the prompt for today is writing a function that takes an array of unsorted integers that will consist of only 0, 1s, and 2s. The function should return the sorted array of 0s, 1s, and then 2s. So for a simple example, 0, 1, 2, 0, 1, 2 should be returned as 0, 0, 1, 1, 2, 2. Simple enough. Longer example of the same thing, bunch more zeros, bunch more ones, bunch more twos, returns a sorted array of those values as well. And we're going to have a little edge case to see if this passes or not, where if there are no twos, zeros, or ones, it should be able to appropriately sort those values anyway and not come crashing down, right? So for some basic history, if you're wondering, again, you could always just pause the video and go check out Wikipedia. This is not the scope of my video to explain all the history, but I do want to give you all some background to it. The Dutch national flag problem is a sorting algorithm designed by Dutch computer scientist Edsger Dijkstra in the 1970s. It is so named because it is inspired by the colors of the Dutch flag, red, white, and blue. The Dutch national flag problem is particularly useful when the input has a high frequency of repeated elements, like our simple example here of 0, 1s, and 2s, as it can sort the array in linear time complexity, a big O of n, that linear line. However, it has some limitations when it works for arrays with a small number of unique values, and it can require a significant amount of memory when sorting large arrays. Overall, the Dutch national flag problem is a useful and efficient sorting algorithm that has been widely studied and used in computer science. It's a testament to the ingenuity and creativity of its creator, Dijkstra, who is widely regarded as one of the pioneers of modern computer science. If you like history and are reading especially about computer science history and the importance of this problem and algorithm, definitely take a minute either now or after this video to go check out Edsger Dijkstra, as well as the Dutch national flag problem on Wikipedia or other YouTube videos. If you have anything that you found particularly compelling, please get in the comments below and link it, because I love learning about this kind of stuff. So, looking at this as people, not as programmers, sorting these numbers out is easy enough. We would just move the zeros to one side, the ones in the middle, and the twos to the right side. Thinking of this and these crazy looking inputs as an analogy, as again, less programmer and more just people looking at this problem in front of us. We're going to pretend that all the zeros and ones and twos in this array are actually a burp hashtag professional, are a stack of cards. And we're going to have a stack of not playing cards, but just cards that consist of red, white, and blue colors randomly put into a deck. Our task from there is to sort them. We want the reds on top, the whites in the middle, and the blues on the bottom. So what we're going to do to sort the stack is we're going to lift the first card. If it's a red, we make a red pile, a white pile, and a blue pile. And once that's all said and done, red, white, blue, boom, the stack is done. A lot of the times you'll also hear examples of this algorithm done with colored balls or spheres or whatever. I'm going to be using cards for this one since I'm a fan of playing cards and analogies of using playing cards. So, like I said, as we go through the deck, we're just going to keep adding to the appropriate sorted color deck and then add them all together. That's what we as people would do given this problem. Like, in an interview room at a table, and I gave you a stack of these colored playing cards and said, sort that. And then that's probably how you'd approach it, right? Our function is going to function much in the same way as that analogy. But I have to expand on this analogy a little bit in terms of programming terms. Because as people, we can just make 3 of those sorted piles and then stack them together. But if we have to sort this array without using that, how can we keep track of where the zeros are supposed to go, where the ones are supposed to go, and where the twos are supposed to go as we're sorting through this array in place? Like, we're not using 3 separate holding arrays to cram them back together later. So now, Imagine we have to have some boundaries. We're going to call them low, mid, and high. Low representing where the red cards go, mid representing where the white cards go, and high representing where the blue cards go. So not just sorting through this stack of cards into 3 piles, but we're also going to be keeping track of where the boundaries of each card are going to go. Okay? So, again, we're going to have 3 empty piles, 1 for each color, go through the stack of cards from top to bottom, picking up each card, examining its color. If the card is red, we place it on the red pile, white, white, blue, blue, just like before. But the difference here now is we're going to keep an additional pile, which will eventually hold a section of the sorted cards. The piles corresponded to the sections before low, between low and mid, and then after high are going to be represented in our function code here in just a second. After the beginning, we're going to place all the piles at the bottom of the table representing our unsorted array. And to keep track of our progress, we're going to use those low, mid, and high pointers. The low pointer represents the end of the red section, the mid pointer represents the end of the white section, and the high pointer represents the beginning of the blue section. So end of low is all the zeros, end of mid and before and after low is all the ones, and then anything after high, so that's the important part there, after high are 2's. As we place each card into the corresponding pile, we're also going to move the appropriate pointer to the right for low and mid, and to the left for high as we build out those sections in the array. Once we've gone through the entire stack of cards, we should have them, again, organized by red, white, and blue, with the pointers being moved in until mid is greater than high, in which case we can stop because then we have our sections completely built out. So that is what we're going to be attempting to accomplish today in this particular code base. So again, it sounds much more complex when you begin adding the programming aspects of pointers into this and having to sort the array in place. So, again, thinking about it, I could go ahead and start writing the code now, but we're going to take this input example of 012, 012, and I have it broken down into a diagram along with our variables and the pseudo logic we're going to be using to write this code out. Then we'll write the code out, and hopefully by then you'll understand what the process is. So let's take a look at this breakdown I have here in this Markdown document. Again, we're developers. I figured making diagrams in a Markdown would make sense. Just like reading code documentation for any library you would ever use. All right. So when we first start our function, clearly we're going to have to set up some initialized variables, and then eventually we're going to be looping through this content because we're going to have to loop through and sort this little guy right here. So we're going to initialize our 3 boundaries, our low, our middle, and our high. Our high will be at the end, aka the length minus 1, which will be 0, 1, 2, 3, 4, and 5. We're going to initialize it as a 5. Low and mid, we have no idea, so we're going to start them at the very beginning at index position 0, and call it a day. That's going to be our initial values, our input array, and then our 3 variables. Then we're going to enter a while loop, and the condition for the while loop is so long as mid is less than or equal to high. Because remember, because high is being pushed in because it represents the afterwards is where all the 2's start, and the mid represents is where all the 1's are, but once the mid pointer passes the high pointer, we stop the loop because, well, all the 1's are done, all the 2's are done, and once these two swap position, we cancel the loop because it should be our sorted array at the end of it, okay? So that is what our loop is going to do. It's going to keep on incrementing high, keep on incrementing mid, keep on decrementing high until they swap, and then boom, we stop the loop. Now, there are going to be 3 conditions. We're going to actually write this as a switch statement, and we're going to be basing it on the value of the mid, because again, low will just kind of increment over time, mid has to increment over time, and high has to decrement over time in order for these boundaries to work correctly. And this is all going to be based on what the current value, not the pointer, the value element is of the mid pointer. So we're going to check the value of the array mid as the condition for our switch statement. Whatever its value is will determine what's going to happen because it can only be one of 3 possible values, a 0, a 1, or a 2. In the event that mid is 0, we know zeros need to go at the beginning or wherever the low section is. So if it's a 0, we swap the low pointer value with the mid pointer value because it's a 0. We swap them, and then we increment both the low and mid pointers, okay? So once again, if mid is a 0, we swap it with whatever low is, swap, and then we increment both low and mid up one section. Okay, so our low boundary has grown by 1, and our mid boundary has technically grown by 1 as well because there was a swap. In the case mid is a 1, well, middle ones need to go in the middle section, so we don't swap anything. We leave the 1 where it is and say, oh, now the mid is going to move up 1 because, well, it's supposed to represent the section of 1s behind it. In the event that the value of mid is a 2, we do the opposite of what we did for the low. We take the 2, which is the value of mid, swap it with whatever our high element is, and then we move high, the pointer, in by 1 because it represents everything after it as 2's. So once again, if the mid value, if the pointer at mid is pointing to a 2, we swap it with our current high value and decrement our high in 1 because now we have a 2 after the high. We have 0s before the low, and we have 1s before the mid. Okay, so those are going to be our 3 cases, and we're going to kind of zoom back up to this every now and again as I kind of take us through step by step of how this is going to break down. So these are our initialized values. The element of mid is a 0, and the value of low is also 0. So let's go on down to the first iteration. Oh yeah, I forgot to put, this is where the pointer low and mid is pointing to. This is where our high is pointing to with our initialized values. So at the first iteration, we swap. Remember, what is the value currently of mid? It is a 0. So we swap low and mid. But low and mid are currently pointing to the same thing, which is a 0. So the 0 swaps in place with itself. Whatever. That's fine. So the 0 swaps in its place with itself, and then low and mid increment their pointer by 1. Boom. So here is where low and mid have now incremented by 1, so now they're both looking at this value, because the low pointer now has everything behind it being a 0. So that's actually very good for what we want so far. Nothing has changed to high yet. Now, the value of mid is 1. What do we do on 1s? 1s, we simply increment mid because it's supposed to represent anything behind mid should be a 1. So that's when we increment mid by 1. The low has stayed here at index 1. We swap nothing, but mid moved up to here. So everything behind mid is now a 1, which is technically true, and nothing has changed with high. Okay, so now for this iteration, mid has a value of 2. What do we do on 2's? On 2's, we swap the high and the mid, and then we decrement the high boundary inwards. So back down here, mid is a value of 2. High is a value of 2, so we swap the 2 and the 2. Doesn't help us, but what does happen is the high should move in 1, and thus it decrements down to 4. So now everything after the high pointer is indeed a 2, everything before the low pointer is a 0, and everything technically before the mid pointer is a 1, so I mean technically it's correct thus far. But because we haven't done anything to the midpoint, we still look at its value. It is still a 2. So what do? We swap the 2, we swap the high, which is a 1, and we move the high in 1. And we get the following, right? 0, 1, 1, 0, 2, 2. So remember, the 2 and the 1 have swapped, so now we have the 2 2's after our high boundary. Bravo, that's already done. And now we've decremented the high in here, okay? So at this iteration, the mid value, the pointer for mid, is a value of 1. What do we do on 1's? We do nothing except increment the mid up 1. So now mid and high are the same value. Oh, well, remember, the while loop is so long as mid is less than or equal to high, we continue our logic. So mid's value is 3, 0, 1, 2, 3. Same thing for the high. What do we do on 0's? We swap it with the low and increment both the low and the mid up 1. Remember, let's back up here to refresh our memories. If it's 0, swap the low and the mid, and then increment the mid and low pointers up 1 together. So this is where we were. It's a 0, so we're going to swap it with this 1 and increment the low pointer up 1 and the mid up 1 as well. So we wind up with a low of 2. Everything before that is 0's. The mid is now greater than the high, which means we stop the loop, but when we stop the loop and return this array, it should be our assorted array, because everything after the high is 2's, everything between the low and the mid is now 1's. So when this value is greater than this, the loop will stop, and we should have a sorted array of 0, 1's, and 2's. Return an array and celebrate. So hopefully this breakdown of each step of our code is going to help understand what we're actually going to be coding here in just a moment. I had a lot more explanations, but honestly, the diagram was the best one I could come up with in terms of seeing variable by variable and these pointers to see where this code winds up. So actually writing the code out is not too bad now that we understand what's happening here. So first things first, let's go ahead and assign our initial values. We had a low of 0, a mid of 0, and our high will be our inputs array length -1 for the final index position of it. Now, let me show you what this looks like using a temporary variable. So I'm going to have an undefined or null, whatever you want for your personal uses. A temp variable we're going to be using to swap indexes or values on the array on like we did in a previous video. I will also use a quick little ES6 array destructure swap to do it as well. But let's use a temp variable to hold an array value as we swap two in place. So, like I said, we're going to have our while loop. So long as the midpoint is less than or equal to the high point, or boundary, I should say boundaries instead of points, or pointers. As long as the mid boundary is less than or equal to the high boundary, this loop will continue. Remember, the switch case for the switch condition is whatever the value of our mid boundary is. Because if it was a 0, low and mid go up and they swap. If it's a 1, stay no swap, increment mid. If it is a 2, swap with the high, decrement the high. So here we go. Case 0. In the case of 0, we have to swap the low and the mid. So I will use my temp variable to store what is currently in the low. That way I can take what's the current low and reassign it to what the mid actually is. And then we're going to take what the mid was and swap it with what the low was, represented by temp. Hence why we're going to use that temp variable. Maybe this will be a bit easier to understand until I throw in the fancy ES6 structure. So that is the swap. Swap low val with mid val using a temporary variable. So remember, we're thinking values here, not pointers. We're swapping the low value with the mid value. Then we increment the low and we increment the mid. And this case is donezo. Right? Easy enough. Now, in the case of 1, even easier. We don't swap anything. All we have to do is increment the mid, and our case is done. Easy enough. In the case of 2, same swap logic, except between mid and high, and then we simply decrement the high by 1. So in the case, the mid's value is 2. We quickly copy the mid value to use later. We're going to say the new mid value is whatever the high value is. Now we've swapped the high over. And then we're going to take the high and say you are what mid was. So this takes high to mid, and this takes mid to high. So that's how we swap them there. And like I said, we then subtract 1 from our high pointer, our high boundary. After all that is said and done, we should be left with the sorted array. And that's, like I said, the code itself is not that bad, like I alluded to at the beginning of this video. It's just that trying to understand how to approach this from a programmer standpoint and these pointers, these boundaries, was a little bit difficult. But hopefully after the diagram and seeing it broken down step by step, my analogy, and hopefully this code here, seeing and understanding it, is not too bad. So let's go ahead and actually call this here and console log one of my inputs to see if she works. Nope, not that. New terminal. What's the command for that? Command shift tilde. Yoink. npm run devarino. Oh, got me, folks. I was like, well, that's not right. That is because I wrote my return array inside of my while loop. Whoopsie poopsies. It needs to be outside of my loop. So after the loop is entirely done, that is when it should console log anything. Gave myself a mini heart attack there because I was like, that's not right. Which, again, happens all the time with my code. We don't get, I say it all the time, you don't get better at not making errors, you get better at understanding what your errors are. So I quickly realized that my return array was in the loop because the purple one I knew was with the loop here for the while loop. Anyway, check it out. There's our lovely looking sorted array. Let's go ahead and console log this one as well, just to confirm it can take an even longer string of them and I'm not just yanking y'all's chains here. Boom. 0s, 1s, and then 2s all sorted out beautifully. And then finally, what if our case doesn't have any 2s at all? What if it's just a joke input that has no 2s, no blue part of our Dutch flag here? Still works just fine. There you go. And I also have a couple tests that, I've been running the tests recently, but whatever. I think the visual is much more important here than a bunch of random tests that will be eventually for this repo that I'm creating here. But yeah, I'm actually, if I make this repo, I'm also going to leave this diagram in here because I think it'll be important for, especially my newbies out there, to try and understand how this whole process works and why we wrote it the way we did for this algorithm, right? So yeah, if we wanted to do this with some cooler looking code, like I said, the temp stuff feels like more old school JS solutions here. So if you want like some really cool, I did this, I think, literally in the previous video, in this playlist of swapping array positions like this. I'll say array low, the new array low and the new array mid will be the array mid value and the array low value. So that's some cool ES6 shorthand array destructuring to swap array values like that really quickly. We can do the same thing for this particular case, because remember, the new mid value and the new high value will be what the array high value was and what the array mid value was. Yeah, save and rerun, and the code runs just fine itself, right? Nothing has changed. For example, making sure I'm not just BSing y'all. Yeah, see, I added the 1 to the bottom, and it gets sorted correctly right up there above my fat head. So yeah, that is the code for this one, along with my cool ES6 destructures. And I probably should say swap mid val with high val. There we go. Yeah, that's this one in a nutshell. So the big O complexity, again, why this is so cool is because it has a big O of n. It is a linear complexity. In this particular case, it's that line. The bigger the input gets, the slightly longer, more operations you're going to have to do for this particular algorithm. The space complexity is a big O of 1. So the complexity is O of n because the algorithm iterates through the array once while using a single while loop. Each element is processed once, and in each step of the loop, we either swap elements or move one of the pointers. The worst case scenario still involves going through the array at least once. The space complexity is a big O of 1 because the algorithm uses a constant amount of extra space regardless of the input array size. The extra space consists of 3 pointers, low, mid, and high, and a temporary variable for swapping elements, or the ES6 destructure. The algorithm performs in-place sorting, means it does not require any additional data structures to sort the input array, right? So, in terms of why it's cool, clearly, if you get asked this algorithm at an interview, you'll at least have an idea of where to start coding for it. If you don't remember exactly how to code it, at least you can describe the process to it. It's seen in a lot of broad concepts when it comes to programming, like quicksort partitioning. The quicksort algorithm can be used to optimize the partitioning process when it comes to duplicate elements and things like that. Colorful classification in computer vision or image processing tasks, you need to classify and sort colors. Hello, that's exactly what we did here. Load balancing. The Dutch national flag problem can be used for load balancing by categorizing tasks or requests into 3 different priority levels: low, medium, high. So like a priority queue. Now you know how to sort an incoming array of priority queues or tasks that have to come in to your machine. You'll see this in DNA sequence analysis. In bioinformatics, DNA sequences can be represented as strings with 4 characters: A, C, G, and T for my biology majors out there like I was. When analyzing or processing DNA sequences, the Dutch national flag problem can be extended to handle 4 distinct elements and help in sorting, searching, or classifying these sequences more efficiently. So overall, it's a very powerful tool that's used in various and common problem-solving situations. So, as always, I hope y'all enjoyed watching this. Thank you for watching. And hopefully, together, we have grown as developers, and the nightmare of me trying to diagram this out step by step is over. So if you enjoyed that, please consider giving us a like, comment, and subscription to our channel for more videos like this. Also, I would love to hear y'all's thoughts if you have cool videos about the history of Dijkstra, the Dutch national flag problem, other videos that cover this with better diagrams, probably someone that has actual visual talent or graphics talent, unlike me. Get in the comments down below and feel free to share. If you have alternate solutions, remember, constructive and positive comments are always welcome here. Let's keep this discussion going and help each other become better programmers. So as always, thanks again for tuning in, and I'll see y'all in the next video.